Hello, welcome to my presentation regarding our recent work off-chain execution and verification of computationally intensive smart contracts. I will start giving brief explanation of what a smart contract is. Smart contract is a software program that resides on the corresponding blockchain network and gets executed once the predetermined conditions are met. In this example, let's assume that Alice would like to buy a product from Bob. However, they do not trust each other. Smart contract can be constructed by coding the required conditions on it. Upon that, they can finalize the transaction seamless and in a trustless manner. Ethereum is the first cryptocurrency that supports smart contracts. However, it has several shortcomings. Ethereum smart contracts are required to be executed by each miner of the network, and every Ethereum transaction that modifies the state of the Ethereum required to pay a gas fee. Depending on the complexity, this fee could get quite costly. As a result of this, application variety of the smart contracts are highly limited and it is infeasible to implement computationally intensive programs such as machine learning and zero knowledge proofs. We call these smart contracts a computationally intensive smart contracts. There has been high interest both from industry and academia to bring a solution to these problems. One line of work requires the program to be outsourced to the computationally powerful set of executors. However, this will duplicate the computation effort across computers that we avoid in our work. Another line of work requires the programs to be executed in a trusted execution environment, namely Intel SGX. However, again we would like to avoid this approach as there have been a different number of attacks on it. Another line of work is the verifiable computation, which I will explain in the next slide. Our work falls into verifiable computation problem. Let's understand the verifiable computation problem with an example. Alice wants to compute computational intensive task, however, she doesn't have enough resources. She can outsource it to a powerful machine and wait for it to compute for Alice. However, once the result is computed, Alice needs to verify whether the computation is performed legitimately or not. Alice can verify the result by re-executing the offloaded computation. However, this will defeat the whole purpose of outsourcing it. Instead, once the result is ready from the powerful computer, it also sends the proof of correctness along with the result. By doing so, Alice can verify the result faster than re-execution of the whole program. In our work, we use the Pinocchio Compiler. It's a tool developed by Microsoft to verify the program's correctness written in a high-level programming language. Pinocchio Compiler takes the given C program and converts it to arithmetic circuit, a circuit representation of the program, then transforms the computation into a set of polynomials called quadratic arithmetic programs, or QAP in short, which will be used to verify the full circuit computation. In our framework, we have Alice, who would like to outsource the computation, and we have Bob, who will work as a worker. And we have broker contract, which is a smart contract that resides on Ethereum blockchain that works as an intermediary between Alice and Bob. First, Alice posts the job details to a server that she controls, and then she creates a job request on a broker contract. Bob, upon seeing this request, will check whether he has enough resources to complete the job. If so, he will assign himself, which essentially means registering for the job, on a broker contract. He will retrieve the files from the service Alice's server and will compute the job locally. And then he will upload the proof along with the result to a server that he controls. And he will call the getPaid function on broker contract. Proof and the result retrieved by the miner and will be verified. If it is correct, Bob will get paid. To verify the effectiveness of our framework, we use four computationally intensive programs, namely matrix multiplication, image matching, multivariable polynomial evaluation, and fluid virtual. Our experimental results shows that the framework provides a quick proof verification for different sizes of input parameters for all applications. The framework also maintains a constant proof size for sizes of 288 bytes in all cases, despite input parameters. As expected, we have noticed an increase in the proof generation time with an increase in the application parameter size, which was due to an increase in the number of multiplication gates and equality comparisons. And that brings us to the end. Thank you.